Hello, my name is Bruce Dorr, and I'm one of the scientists that works here at Science North. In this video, we're going to look at the concepts of light, optics, radiation, and specifically ionizing and non-ionizing radiation. So you might hear the word radiation. Oh no, we might think of nuclear, waste products and things like that. But radiation is a general term that we give for any forms of energy that are within what we call the electromagnetic spectrum. And there's many, many different forms of energy within that spectrum, going from radio waves, microwaves, infrared, visible light is part of that spectrum, ultraviolet, X-rays, all the way to gamma rays, all right? So there's many, many different forms of radiation and energy. Now, what's really interesting is that some forms of this radiation will have more energy than others. So what we're gonna do is we're gonna do a very quick experiment. So I have some fluorescent paper right here. And what's neat with this fluorescent paper is depending on the amount of energy you put in, if you put in lots of energy or energy with high level, or light with high levels of energy, it will then fluoresce and give back light. So let's try two different forms of light. So I have a laser here with green light, and we're going to see what happens with the green light here. All right. So we see no fluorescence. So it's probably very low energy. Now let's try with this light, more in the UV range. And if we see, look at that, it's actually fluorescing. So what this tells us is that UV light has more energy than green light. So what does that mean? How is that related to ionizing and non-ionizing radiation? Ionizing radiation is radiation that has high levels of energy. Essentially what ionizing radiation will do is will knock off an electron, so much energy will knock off an electron from an atom or a molecule, causing it to become an ion. Non-ionizing radiation doesn't have that much energy, cannot knock off an electron, and therefore does not create different ions, okay? How come we have different levels of energy? Well, it all depends on the wavelengths. If you have wavelengths that are very long, like radio waves or microwaves, very low energy level, non-ionizing radiation. When you have wavelengths that are very short, it means they have high levels of energy, so we are dealing with ionizing radiation, okay? So that's how we can tell the difference between the two. And when you actually look at this, from ultraviolet X-rays to gamma rays, you're increasing the order of magnitude, the amount of energy that's there. And it's not to say, these types of radiation, we should, take them lightly. For example, gamma rays, a lot of people think, you get a dose of gamma rays, and next thing you know, you're kind of green and very, very angry. Well, that's not how it works. Gamma rays have so much energy, it can actually destroy DNA in your cells. You can actually get radiation sickness, and you can have some severe burns, all right? So it's not what we see in the comics. So what I want to do right now is show you a piece of instrumentation that we have here at Science North, which will help us visually see the different forms of radiation, and specifically ionizing radiation, high-level particles or energy that actually bombard our planet. Come with me, I'll show you that piece of instrument. So this piece of instrumentation is called a cloud chamber. It is made up of supersaturated alcohol in a vapor form. Now, what's really neat with this instrument, it can actually detect ionizing radiation. So when high energy particles hit this cloud chamber, what happens, it will ionize some of the vapor molecules. And by ionizing them, what happens, the vapor molecules will have a charge. And then the other vapor molecules will be attracted to it, and the end result of this, you actually see a cloud or a streak. So what you see right now is a whole bunch of streaks coming from high energy particles or ionizing radiation. And where these different forms of radiation are coming from? Well, it's actually coming from space and also from the sun. So I will do a quick demonstration. I have a piece of radioactive material, gamma ray. And by putting on there, we're going to see a change on what we're seeing here in the number of streaks that we can see. So what this is actually telling us is that we actually have different forms of radiation, ionizing radiation, emitting from that, hitting the cloud vapor. And what we're actually seeing right now is a whole bunch of streaks caused by this ionizing radiation. So ionizing radiation and non-ionizing radiation is found all around us, and it is just part of life. So let's look at ray diagrams a little bit more closely. And we're going to use two examples of telescopes to really see ray diagrams a bit up close. This type of telescope is actually called a Newtonian telescope. And what's really neat is that the light comes in, hits a parabolic mirror, it comes back, hits a flat mirror that then goes up an eyepiece. So if we see, I have a light hitting right there, goes into the telescope, and then comes out right here. This type of telescope is very, very different. It's a Galilean telescope. Essentially, it doesn't use mirrors, but in fact uses lenses. So light comes in. So I got some light coming in here, goes through a set of lenses, convex lenses, and then through another set of lenses, and then comes out here. Now, the trouble about using lenses is as light goes through lenses, it's a bit like a prism, it will actually cause parts of the light spectrum to kind of diffract and kind of segment. So what you need to do is you need a double lens right here to deal with what is called chromatic aberration. If you don't have that, then your image doesn't look good, it gets kind of fluid, and then another set of lens right here to deal with that. So it's called a doublet or a doublet set of lens to deal with chromatic aberration. So what we're going to do now is that we're going to see how the different light rays actually go through the telescope using a special type of machine, a fog machine. So I'm going to grab the fog machine. I'm going to show you right now. All right, so here's my fog machine. So let's see what happens when I put it on the telescopes. Pretty cool. So what we're seeing is a very simplified ray tracing of both telescopes. When you actually do ray tracing, what you usually do is you take all the different wavelengths of light or a different light as it comes down into the different telescopes in order to give an image. The reason why we're only seeing one ray or one line in this case is because we're using lasers. And lasers will concentrate all the wavelengths of light into one single point, and that's why we are seeing this one single line right now. So it's not something that's like abstract, it's real, and you can actually use ray tracing to see how light bounces off surfaces and where it ends up.